Hello everyone and welcome to the class on circuits and networks, and today we are going to deal with the class on maximum power transfer theorem. So that was what the previous two videos were about, but the only change over here is that we are going to deal with the maximum power transfer theorem for AC circuits. Okay, so the previous two theorems we had studied were Thevenin's theorem and Norton's theorem, and we had seen that while coming to AC circuits, there's not much change for Thevenin's theorem as well as Norton's theorem. But when you come to maximum power transfer theorem, there is a small change in DC circuits and AC circuits. It's a very small change. Right. Now, when you come to DC circuits, we had studied that the maximum power is transferred from the source to the load when the load resistance is equal to the source resistance. So this was the condition for DC circuits, and this was for maximum power transfer theorem of DC circuits. Now, when you are coming to AC circuits, we are going to have not resistance, but you are going to have impedance. Okay, so we need to know for what value of the load impedance the maximum power will be transferred from the source to the load. So again, we have just drawn a Thevenin's equivalent model over here, and you can see there is a source Vs and there is the source impedance Zs. Then you are having the load impedance Zl, and we need to find out for what value of Zl you will get the maximum power transferred from the source to the load. Okay, so the condition is a very simple condition. So the load impedance, we know that the impedance can be written as R plus J into X. Okay, so here we are writing RL plus JXL. Here XL is not the inductive reactance, it is simply meaning the load reactance. Okay, please don't get confused. Okay, so we know that this is the general format for impedance, R plus J into X, where R is the resistive term and X is the reactance. So the reactance can be inductive or capacitive. Now here, as I mentioned before, this is representing the load reactance. Okay, it's not the inductive reactance, it's the load reactance. And this value, the value of load impedance, for what value of load impedance you will get the maximum power transfer. So when the load impedance is equal to the complex conjugate of the source impedance, you will have maximum power transfer theorem. So that means the complex conjugate means Zs can be written as, you can see over here, Rs plus J into Xs. Okay, so this is source impedance with the source resistance and source reactance. So this ZL, when it is equal to the complex conjugate. So complex conjugate of a complex number means you just replace the positive with the negative. So that means it will be Rs minus JXS. Okay. So sorry. So the load impedance, when it is equal to the complex conjugate of source impedance, you will get the maximum power transferred from the source to the load. And you can just go through the derivation. It's a very simple derivation, so you can just go through the notes which I have previously shared. I'm not going to do the derivation over here, so I want you to complete the derivation in your notes. Okay, the derivation is very simple, so you can just complete the derivation in your notes, and with that you can just tell me whether there are any confusion, so I will explain it to you. Right, so we can move on to the problem. So you have a problem over here. You need to find the value of load impedance for maximum power to be transferred to the by the source to the load, and also you need to find the value of maximum power transfer. So the procedure is the same. Okay, the steps are the same. Only there's a small change in the second step. That means when you had DC circuits, the first step was to find out the Thevenin's resistance. So here you are going to find out the Thevenin's impedance. And then the second step is to find out the value of the load resistance. And for DC circuits, the load resistance was equal to source resistance. But in this case, the load impedance will be equal to the complex conjugate of the source impedance. Okay, so we can just go through the step 1. We are going to find out ZTH. So in order to find out ZTH, here you can see you have to remove the load, and if there are any sources present, you need to deactivate the sources. So what I'm going to do over here is that I'm going to deactivate the voltage source and I'm going to replace it with a short circuit, and you have to remove the load impedance as well. So I'll just redraw the circuit over here and just draw that quickly. Having a capacitor, inductor. Alright, it's a simple circuit. And we need to short circuit the voltage source. So you have 2 ohm, 8 ohm, J5 ohm minus J12 ohm. And we need to find the value of the Thevenin's impedance. So it's quite simple. So these are your terminals. So you start from the opposite side and you can see these two, they are connected in parallel. So I can replace this with an impedance. So what will be the value of the impedance? 2 parallel J5, and again this is your circuit with minus J12 ohms over here, and again if you are reducing it, so you can see these two, they both are in series. So I'll just again reduce the circuit over here. So this will be 8 plus 2 parallel J5, and finally you can see that these two, they are in parallel. So I can finally write ZTH is equal to, so if these two are in parallel, you have minus J12 is in parallel with this value 8 plus 2 parallel J5. So you can just solve it over here. Minus J12 ohm is in parallel with, so if you are solving this, you are going to get the value. I have already solved it previously. Okay, I only have the final answer with me. So if you are solving it, so you will get, I'll just take my calculator real quick. So you can solve it along with me. You can take the complex mode in your calculator. 8 plus, oh sorry, so it will be 2 into 5j divided by 2 plus 5j, and you are going to get 8 plus 1.7, it's not clear, plus 1.724 plus 0.689 j, and you can just solve this. So you can just add it. It will be 8 plus 1.7 will give you 9.724, and these two are going to be in parallel, and you will get the final answer for ZTH as 6.29 minus 4.67 j. So this is your value of ZTH. Now once you get the value of ZTH, so your step 2, you need to find out the value of the load resistance. Okay, you need to find out the value of the load resistance, and if you want to find out the value of load resistance, I had already mentioned the load resistance or load impedance, sorry, not resistance, impedance will be the complex conjugate of the source resistance. And how do you find out the complex conjugate? So the source impedance is same as ZTH, so that means you need to take the complex conjugate of ZTH. So if you want to find out the complex conjugate, you just replace this sign with the opposite sign. So that means I need to write it as 6.29 plus 4.67 j. So this is your load impedance. And next we need to find out the value of VTH. Why do we need to find out VTH? Because we have completed the A part of the circuit, but we need to do the B part of the circuit, the question. That means you need to find out the value of maximum power transferred. So in order to find out the value of maximum power transferred, we can just come to the original circuit. If you want to find out the value of maximum power transferred, you need to remove the load impedance and then find out the value of VTH and draw the Thevenin's equivalent circuit. Then you can find out the value of maximum power transferred. So I'm just going to redraw the circuit on the next page. So I'm just going to write the third step. step 3. So you see only the second step has changed. Instead of taking ZL is equal to ZS, you have to take ZL equal to ZS star. But all the remaining steps are the same. The step 1 is the same, step 2 is the same, and step 3, step 2 is not the same, step 3 is the same. So I need to find out VTH. So I'm just going to redraw the circuit over here. Right. So I'll just redraw the circuit. You have two resistors, a voltage source, an inductor, a capacitor over here, and the values of the resistors are 2 ohm and 8 ohm, and you have minus J12 ohm and J5 ohm and 10 angle 0. Okay, so we need to find out the value of VTH. So as mentioned before, whenever you want to find out the value of VTH, so you can see VTH was over here. So VTH is simply the voltage across this particular capacitor. So obviously the first step is we will be applying the mesh analysis. Okay, so you have two meshes over here, mesh 1 and mesh 2. And I'm going to apply the mesh analysis. So I'm going to write the mesh 1 equation. So you have 10 angle 0 minus 2 I1 minus J5 into I1 minus I2 is equal to 0. Or I can also write it as minus 2 minus J5 into I1 plus J5 into I2 is equal to minus 10 angle 0. So as I had already mentioned, it's always better to avoid this negative sign along with this polar format. So I'm just going to multiply throughout with the negative sign. So on multiplying throughout with the negative sign, you can see that I got this value as positive, and this is my first equation. So next I'm going to write the mesh 2 equation. So you have minus J5 into I2 minus I1 minus 8 I2 minus of minus J12 into I2. So I hope it is clear why I have written minus of minus Ji2. Okay, already you have to give a minus for the mesh analysis, and this minus is that of the capacitor. And if you're rearranging over here, you're going to get it as J5 into I1 minus 8, or I'll just write plus, right, minus 8, and this would be yeah, so this would be plus 12 and minus 5, so that will be 7, right? So it will be plus 7 J I2 is equal to 0. So please excuse me, I hope I haven't made any calculation mistakes over here. Right, so I think it's correct. So that's my second equation. Okay, so we have applied simply the mesh equations. This is your mesh 1 and this is your mesh 2. Now, so we need to find out the values of I1 and I2, and I have already mentioned that in your calculators you cannot solve the complex equations. So it's better to use the Cramer's rule. Now, you need to use the Cramer's rule, but you just look at the circuit again. That is whether you need to find out both the values of I1 as well as I2, whether both the values are required. Okay, we need to find out the value of VTH, and VTH is simply the voltage across this particular capacitor. Okay, and how can you find out the voltage across the capacitor? So you can see the current is going in the downward manner. This is your polarity, so definitely VTH is equal to voltage across the minus J12 ohm capacitor. And how can you find out the voltage across the J12 ohm capacitor? That will be minus J12 into I2. Okay, so your VTH, basically your VTH is not depending on the current I1. So I simply need to find out the value of I2. So in order to find out the value of I2, we are going to use our Cramer's rule. Oh, sorry, it's a C. Okay, anyways, we are going to use our Cramer's rule. And how can you find out use the Cramer's rule? You can write down the equation in the matrix form. So you have 2 plus j5 and minus j5. Then you have plus j5 minus 8 plus 7j. And you have a column matrix I1, I2 is equal to 10 angle 0 and 0. Our aim is to find out the value of I2. We are not bothered about I1. And how can you find out I2? So the denominator will be the same matrix, the determinant of this same matrix. So you have 2 plus j5 minus j5 and j5 and minus 8 plus 7j. And in the numerator, you just check out, you need to find out the value of I2. So if you want to find out the value of I2, you replace the second column with the column matrix. The remaining columns will be the same. So that means 2 plus j5 and j5 is not changed. And instead of this second column, you are going to give 10 angle 0 and 0. You are going to replace this column with this column matrix. And you can simply find out the determinants in your calculator. So it will be this into this is 0 minus 10 angle 0 into j5. So don't forget to give the brackets, divided by 2 plus j5 to minus 8 plus 7j minus, and here you can see there's a minus over here, so that will be j5 into j5. Okay, so on solving you will get the value of I2. So your value of I2 is going to be 0.622 angle 71.11 ampere. So I just want you to calculate this and check it out whether the answer is correct. You just solve it in your calculator and you find out the value of I2. So this is our Cramer's rule. And once you get the value of I2, you can substitute it over here for your in your equation for VTH, and you will get the value of VTH as 7.469 angle minus 18.88 volt. So this is VTH, right? And last but not the least, so we have completed the first step, that is finding out ZTH. The second step was to find out the load impedance, and we have done that. The third step was to find out VTH. And finally, the last step is to draw the Thevenin's equivalent circuit. So our step 4 is to draw the Thevenin's equivalent circuit and find out the value of Pmax. So how can you get the value of Pmax? Pmax is simply VTH square divided by RL plus RS, I forgot to mention that over here. Right, I forgot to mention that at the beginning. So if you want to find out the value of maximum power transfer in the case of AC circuits, the maximum power transfer Pmax is given by Vs or VTH square into RL divided by Rs plus RL the whole square. I forgot to mention that at the beginning. So you can just note this down as an important equation. The equation for Pmax is Vs square into RL divided by Rs plus RL the whole square. So if you just go through the derivation, you can see this particular equation. So coming back to our problem, you have VTH square into Rs plus RL the whole square into RL, and I'll just draw the Thevenin's equivalent circuit over here. So you're going to have a voltage source, you're going to have your ZS. You can just write out the values. I'm not going to write out the values, you can just complete it. And this is your ZL, and you can just substitute, as I mentioned, you can substitute the values over here. And once you substitute the values of RL, RS and RL, so what is the value of RL? You might be wondering. RS and RL, you will get it from this ZTH. Okay, so I think it will be better if I just write the value here for making my explanation easier. So it is 6.29 minus 4.67J, and here it is 6.29 plus 4.67J. So RS is simply the real part of ZTH. Instead of ZS, I'll write here ZTH. So RS is simply the real part of ZTH, and RL is the real part of ZL. So you can see RL, RS and RL, they are always the same. And on substituting the values in the equation for Pmax, you already know the value of VTH also, that is 7.469 angle minus 18.88. We are only bothered with the magnitude when you are substituting over here. Okay, we don't want the angle, we only want the magnitude. So you do the substitutions and finally you will be getting the power as 2.217 watt. So this is the value of maximum power transferred to the load by the source. And again, as a homework, I want you to do this particular problem. It's an easy problem, and while doing the homework you can just note over here that you are having, this is a current source. You see there is an AC sign over here. Okay, and there is an arrow. Oh, I think this question is incomplete. I haven't written the value. It is 50 angle 0 ampere. Okay, so it is a current source, not a voltage source. So it's very similar to the problem that I have given yesterday. Yesterday it was a DC circuit and today it's an AC circuit. That's the only difference. So I want you to complete this as your homework. So thank you everyone for watching the video. So that's about it. If you have any doubts, you can always contact me. Thank you.